Hi guys, Dr. Mattis here. Hey, I just want to sort of wrap up covalent bonding and structures and all this jazz that are in this series of videos with a final little talk on hybridization. Don't worry, it won't take long. Hybridization is what you sort of get when you do molecular orbitals. Molecular orbitals are just like atomic orbitals, the regions of space that hold up to two electrons, except instead of being in an atom, it's in a molecule. Atomic orbitals are in atom, molecular orbitals are in molecules. Molecular orbitals can be a little bit more complex because molecules, let's face it, are just a bit more complex. Okay, so for atomic orbitals, you memorize them a little bit. You know, they're s, p, d, and f. Those are the sublevels. We don't really talk about the particular p's or the particular d that you need to talk about. Well, for molecular, you don't have to memorize them. You sort of derive them every time based upon what orbitals are combining in the molecule. The molecular orbitals are the little bit that's in here. So if you have an atom, okay, I know that's a crappy explanation, but say we have an atom, and right here's one electron, and the other atom we have another electron. If they're going to come together and bond, then that overlap within the electron cloud between the two nuclei, this groovy little overlapping space between the nuclei, where the electrons hang out, that's an orbital. It's a region of space that holds up to two electrons. Those orbitals, you usually get, when you combine two atomic orbitals, you get one that's just a little bit lower in energy and one that's higher in energy. And we're not really going to talk about that too much, except for the fact that, hey, what do we call that hybridized orbital? The blending, the blend of the two atomic orbitals, the hybrid. That's all we're talking about. Can you identify the hybrid orbital? Okay. Well, hybrid orbitals really depend upon what's being blended. Okay, and so if you take an atom, you look at all the atomic orbitals that have been used for bonding. That is how you determine the hybrid orbitals. So not just the one electron that's being bonded. I kind of alluded to that up here, but we're not going to look at all the bonds the atom is making. Okay, the only difference is you got to keep in mind like double bonds are a little bit more unique. Okay, p orbitals are different. They don't blend. They can be blended, but p orbitals are used for double bonds, and we'll talk about double bonds in a sec. Okay, the double bond, sec is now. You have sigma bonds, which are the original connection, and the double bond, that's the extra. I mean, just think about it. Say you have a C double bond C. You have two pairs of electrons. You have this pair, okay, and you have the groovy green pair. All right, well, if you draw your groovy little Venn diagram gig, all right, where you have the pair of electrons being shared, that initial sharing between the two nuclei, that is called a sigma bond, lowercase Greek letter sigma. All right. Well, remember, that is an orbital, the region of space. It can only hold two electrons. Well, where are you holding on to the other pair of electrons? It cannot fit in that same region of space because that would violate everything we know about orbitals. Well, what you use is you reach around it, above and below it. You can go up here and down below, above and below, and that's what I got going on up here with the orbital that can do that. Is a p orbital. It has two lobes. You can reach around it, give it a big old bear hug. Okay, and so the pi bond exists above and below that groovy little sigma bond. Okay, so just kind of need to know that. If you go on to study organic chemistry and things like that, it matters. That's why you can have resonance. Pi bonds are different than sigma bonds and stuff like that, but don't sweat it right now. All right, let's look at the hybridization of three different molecules of the central atom of those three different molecules. If you look at their structures, these are ones that we've done in previous videos. You have carbon as a central atom, iodine as a central atom, and sulfur as a central atom. Alrighty, so three different central atoms. Alrighty, carbon, it looks like, has three guys attached. One, two, three. So it has a pi bond, that double bond. Iodine has lots of things attached. Okay, and sulfur, a whole bunch more too. So let's take into account that carbon has three atoms attached, no lone pairs, so it needs three orbitals. Okay, and as its s, a p, and a p. We're going from low energy to high energy. Remember, you have s orbitals, and then the three p's that are higher in energy. If you're talking about expanded octets, remember the d orbital is higher for that one. Like if this was the 3p, I'm sorry, the 3s, it's awful. If this was the 3s and this was the 3p, well, the 3d is higher in energy. It's between the 4s and the 4p. Okay, so That's why we go S, P, 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 then add in Ds. So if you look at iodine, it needs 6 orbitals for 6 pairs of electrons, so we take 6. Sulfur, we take 5 for those 5 things attached. 1, 2, 3, 4, 5. Carbon, 2 bonds, but only 1 atom attached via a sigma bond. Sometimes students get confused with that, so I tell you, hold onto your pencil with 2 hands. 2 attachments, still 1 pencil. There's 1 oxygen, so it's spp. So the hybridization would just be sp2 for the 2 p's, sp3d2, 3 p's, 2 d's, sp3d, s, 3 p's, and a d. Cool. That's all hybridization is, just in accounting for all the pairs of electrons that are surrounding the central atom. Alrighty, practice it, learn it, love it. I'll definitely talk to you later. Take care.